guys. Okay, so yeah, thanks for having me here. I'm Sir Lionel Garcia from the University of Liège. I'm a second year PhD student, and I will be talking about a study which looks similar to the previous one, but concerning Trappist-1h and the transmission spectrum we just got. And hopefully this would have led to knowing better the star, but you will see if that's the case or not. So Trappist-1, a bit of context first. So Trappist-1 is an M8 ultracool dwarf. It is 9% solar mass, and it is orbited and even better transited by 7 telluric planets. To the right, you can see the K2 Lie curve. So it's from Luger 2017, and it helped confirming and discovering some of them. To the bottom right, you can see the gray illustration here, the gray zone in the illustration, and you see that 3 of the planets are in there. It's actually the habitable zone, which is making this system even more unique. And looking at the star, its temperature, its size, you understand that these 7 rocky planets are amenable for atmospheric characterization with the James Webb Space Telescope. So what do we know about these planets so far? Not a lot, but what we would like to know at first is if they retain or not a primary atmosphere, so hydrogen-dominated one. We know it is not likely for B, C, D, E, F, and G in the case of a clear one. For a cloudy one, we don't know yet for D, E, and F, and mostly this is coming from Hubble Space Telescope measurements. But today we do not have yet any picture for Trappist-1h. So Trappist-1h is the outermost planet. It receives the lowest irradiation, meaning it's also the most likely to have retained such an atmosphere. Hopefully we have some now, and that's what I will present. So we have some transmission spectroscopy with the Wi-Fi camera 3. We have 3 visits, so 3 transits of Trappist-1h obtained with the GRISM 141, meaning that we have spectra which are time result, extremely interesting measurements. What you see here is the white Lie curve. So the white Lie curve will be obtained by going through the reduction of the raw products in 2 different ways, only to remove a bit of the bias of our analysis. And then, as it was mentioned before, we have a lot of systematics to consider. For that, we use a technique developed in Wake 2016, 2018, which is considering a grid of models simply and comparing one with the other using some inference criteria. Once we are set with the systematics, we can move on and within the Bayesian framework, do the inference. So here we let the radius free, okay, no strong prior. And we have these 3 different spectra. The first thing we notice, of course, is a lot of variation from one to the other, yet we don't know if this is astrophysical or not. Also, I forgot to mention, but of course, here, what we noticed is no obvious spot crossing. And in the spectrum, the combined one, no trend that is also obvious on the spectrum itself, meaning that we would have to consider probably unocculted active regions. Anyway, what we can say from these measurements before going on is that they are robust to reduction techniques, they are robust to the systematics model, we tried many, and the transit time variations, which are important for the Trappist-1 planets. So this is quite important for us because it will lead to precise transit times and a better study of the dynamic of the system. So as I said, we have to turn ourselves to unocculted regions. For that, we will then study the stellar contamination. And we use this model, so it has been mentioned a lot here, but I wanted to make this nice illustration. You know it better than me. It is about modeling the photosphere and considering the heterogeneities as portions of photospheres, full photospheres, at different parameters, especially here, different temperatures. So for the spot, the cooler component and facula, hotter one. To the very bottom, you can see the spectra of what these components would have. For this, we use the Phoenix BT-Sittel model. Why is that? Just because, of course, they should be more suited to the temperature of our star. But here, something really to mention is that, at least in my opinion, this is already a very strong assumption in terms of modeling. And you saw yesterday, especially in Ben Rakam's talk, that picking a model is already something that looks like a prior, because you saw these discrepancies between one model and another. But that said, we have a lot to do already with that. We can apply different combinations. So of course, the first thing we would like to see is what is a pure photosphere looking like. So here what I'm showing is the out of transit spectrum of Trappist-1 observed with the HST in the HST and a fit to the model that I described before. So a pure photosphere, what we get as a best fit is 2575 Kelvin. It is close to what has been found in previous studies. Here, we have to mention that for this pure photosphere, we use a scaling factor on the radius and mass, which should be accounting for error in the model, spectra models. But of course, this is also a strong modeling assumption. And if we will not have done that, which was introduced in WAG for 2018, we will have a big discrepancy. Let's move on to the two components model. So for this one, we keep a pure photosphere, but then we allow for one component, either cold or cool. And what this model is giving is a pure photosphere with a temperature which is similar than the previous one, and actually a colder component, so 37% of cold spots, 500 Kelvin cooler than the pure photosphere. Another point here is that, as you can see, we added some magnitudes. These are priors. And if we would have not done that, we would have something which is more leading to 3% of very, very hot facula, 6,000 Kelvin facula. But it would not have been compatible with the visible magnitudes that have been observed. And that's why we added them afterward. And thanks, Ben Rackham, for pointing that, by the way. And then we have the three components model. Again, really interesting. So this time we allow both for a cool and a hot component. And we have something which is quite similar, meaning 34% of cool spots, plus this hot component, which is here at almost 6,000 Kelvin, but with a very small, thank you, with a very small covering fraction. And about this covering fraction, we wanted to make a point is that this one is actually nice because it's compatible with the model that has been able to explain, so by Brett Morris, 2018, to explain the difference in amplitude when looking the variability through Kepler and Spitzer. So this, as you can see, this is quite compatible. Of course, we do not have the same temperature, but we have such a small component, and the error is accounting for this nice model that was able to explain something which was not explained before. So that said, we can move on. We have our transmission spectrum. We have some idea about the photosphere, and we would like to answer this question. So the model that was the most significant statistically was the two-component model. That's the one we decided to pick. And as you can see to the bottom, it is actually also consistent from one visit to another. So we decided to apply it to the combined spectrum itself. After a quick correction, you can see that we do not have a strong difference, and making a raw comparison with a clear hydrogen-dominated atmosphere, we actually can rule it out to more than 3 sigma. Of course, this is very preliminary. There are a lot of scenarios to try, a lot of atmosphere to rule in, rule out, and this is ongoing. So here is the conclusion. We got 3 transits, 3 visits, no spot crossing event, not obvious actually. At least what we can say, our measurements are robust, so the measurements we can trust. From what we see, we will say that we are leading to a 2-component photosphere with 35% of cool spots. And finally, we are more or less able to rule out this hydrogen-dominated atmosphere that we would have think of. Thanks a lot.
Excellent, thank you. So we have a couple questions. Let's see, I'll start with the one. The visit 4 doesn't look like it has pre-ingress observations. And do you find that this might have an impact on the recovered spectrum? This is a question from Billy.
Yeah, but I think it's a very good question, and we wondered about it, but I don't think it has an impact. And why that is just because actually the model with and without transit time variations, it will shift this visit, for example, but it's leading to the same transmission spectrum. So that's why we said we were robust to these transit times.
And another question, visually the 1, 2, and 3 component models look fairly similar. What were the steps that you took to identify the 2-component one as the best fitting one? And I have a question that I'll just add on to that, which is that did you check the 1 and 3 component models for how those looked in terms of the recovered transmission spectrum in the end? did they look significantly different in the end than the two-component model?
Yes, so the first question really quickly is just about some inference criteria, but that actually proxies of the real bias criterion. So I would say it's just really applying an inference criterion. It's not really fair. But concerning the second question, which is more meaningful, I think, here, is no. So basically, if you take the three-component model with this 6,000 facula at 60 ppm, 20 ppm, you do not have a strong contamination. It's almost flat within the HST band. This was shown in Ducrot, I think, 2018 from the Brett Morris model. So these three models, they will lead to a really minor correction in the transmission spectrum.
Excellent, thank you. There's one more question in the Slido that I'll leave you to answer afterwards, and we will move on to our next speaker.